Dear students, good morning. So today we are going to start the lecture series on this uh, remaining syllabus. Okay. Now let us start with this third unit remaining part. So in the third unit first part, we spoke about data representations. You know that, right? So in order to do computation with any computer, the data must be represented in formats, right? So generally we use two formats for representing the data. So one of the format is fixed point format, you know this, okay. Another format is the floating point format, okay. So okay, so you know that how to represent data in the fixed point format and the floating point format, as we discussed in this previous part of the unit. Now we are going to continue with this. So once we represent data with the fixed point and floating point, okay, now we are interested in how to perform the basic computer arithmetic. So in this unit, in this part of the unit, we are going to focus on, once we represent data with fixed point and floating point, how to perform the basic computer arithmetic, okay, how to perform the basic computer arithmetic. So for performing basic computer arithmetic, in the sense, for performing, if we represent data in fixed point, okay, how to perform addition and subtraction, how to perform multiplication, how to perform division. Similarly, when you represent data in the floating point, how to perform addition, subtraction, how to perform multiplication, how to perform division. So for doing this basic computations, we are defining an algorithms. So these are the algorithms which we are going to implement in the hardware. These are not implemented in the software. Remember that these algorithms are implemented in the hardware. Okay. Now let us see what is the definition of an. Let us start with this. Let us see what is an algorithm. Okay. So you know that what is an algorithm. So 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 let us see the definition of an algorithm. Okay. So what is a basic algorithm? You know, right? The solution to any problem is stated by a finite number of well-defined steps. Right? A finite number of well-defined procedural steps is called an algorithm. Right? So definitely, usually an algorithm will contain a lot of number of procedural steps which are dependent on the results of previous. So this is okay. So basically, these algorithms are represented with the flow chart. You know this, right? Represented with the flow chart. So in this flow chart, you know that, as you know that, the computation is represented with the rectangular boxes. Okay. So the decision, so you want to represent any computation. For example, I want to represent z is equals to x plus y. So this is represented with the rectangular boxes. Also any decision making means, for example, if x equal to x is less than 0, I go this path, x is greater than 0, I go this path, right? Or if x equal to 0, I go this path. So like that, the decision computation is represented with this rectangular, with this diamond shaped, not it's with this diamond shaped box. So this is the basics of what is algorithm. Now in this video, the main agenda is, so before starting the algorithms concerned with the, okay, concerned with this hardware, so let us see the what are the basics in this. Okay. So to understand the basics, the first basic is, I have, suppose I have two numbers. Okay. For example, I represent x equal to 84 in decimal, right? Similarly, y equal to 67 in decimal, right? So if I represent this in the binary, okay, so this is 1010 100 in binary. Okay, you want to, you know this, how to how to do this kind of representations, right? Similarly, if I represent 67 in the binary, so it is like 1000011, right? So now my agenda is, I want to compare these two numbers, right? I want to compare these two numbers, and I want to tell whether, okay, x is greater than y, or x equal to y, or x is less than y. Okay, I want to do this comparison of these two numbers, right? So generally, like I want to do comparison of these two numbers x and y, right? Now in order to compare these two numbers, right, what is a method you know in the DLD, in the digital logic design subject, what you know? So you use a digital hardware called, okay, digital comparator. Okay, use a digital hardware called digital comparator. You can use it inside this, you can run some digital logic, right, and you can apply this x and y as an input, right, and this hardware based on this digital logic, it will take the decision that whether x equal to y, right, or x is less than y, or x greater than y, right. So if x equal to y, this bit will be 1, okay, or if x less than y, this bit will be 1, if x greater than y, this bit will be 1. Accordingly, based on this result, you can interpret that, right, whether the result is whether to compare the two numbers. But in a so this is one method, but if you want to implement this in the algorithm in the hardware, so you need to use the comparator. So can we use this, can we do this comparison without using the hardware? That is my question, right? So without using comparator, can we do that, right, without using this comparator? Yes, we can do that. So how to do that? So without using comparator, how to do that? So we can avoid this comparator by use of 2's complement, okay, 2's complement subtraction, right, using 2's complement subtraction method, right. So what is this 2's complement subtraction method? Let us see here. Okay, for example, you take the same numbers and I'll explain this thing, right. Now okay, for example, let me write again here x equal to 1 0 1 0 1 0 0, this is equivalent to 84 in decimal, right. Similarly, y equal to 1 0 0 0 0 1 1, this is equivalent to 67 in decimal, right. Now for example, okay, I'll do this x minus y, right. For example, I'll do x minus y, okay. So what I need to do, you want to my intention is to compare x and y, right. So here you know that x minus y means, so here you know that if I want to compare x and y, 84 is obviously 84 is greater than 67, but how to know this? For that what we do is we do this x minus y, right. So to prove this we do x minus y, right. So x is nothing but, you know, this x 0 1 0 1 0 0. So here we have minus y, right. So you know that x minus y is nothing but x plus 2's complement of y. So you need to take here the 2's complement of y. What is 2's complement of y here? So 2's complement of y is nothing but, I told the method what you know. So first one you write as it is, first one, then you complement all the remaining words. So 1 becomes 0, 0 become 1, 1 1 1, and this becomes 0. So this is the 2's complement of y. Now you write the 2's complement of y, 0 1 1 1 1 0 1. Now instead of subtraction you perform now addition, right. Do the addition, right. So 1 0, so 0 plus 1 0 plus 1 0, 1 plus 1 0, carry will be 1, right. 1 plus 1 0, carry will be 1, 1 plus 1 1, carry will be 1, 1 plus 1 0, carry will be 1, 1 plus 1 0, carry will be 1. So finally you got an end carry of 1, right. So if you get an end carry of 1, right, the interpretation is x is greater than or equal to y, right. So this is the meaning of this. So what I am doing, I want to compare the two numbers. For comparing the two numbers, right, so if I do the 2's complement subtraction, right, so if I do this 2's complement subtraction and if I get a carry, so if I get a carry as 1, the end carry, I need to look into this end carry. So carry out of this bit, MSB bit. So if I look into this end carry, since it is 1 here, the end carry is 1, then the interpretation is x is greater than or equal to y, right. Similarly, you do this method, y minus x, right. Here y you write directly, what is y here, 10000, okay, 011. Similarly, x means you need to take the 2's complement of x, okay. What is 2's complement of x? So you write 0 0, so you write first non-zero as it is, then you take the 2's complement, 1 0 1 0. Now this is y, you take the 2's complement of x, right, 2's complement of x. What is 2's complement of x here? 2's complement of x is 0 1 0 1 1 0 0, okay, and do the addition now. If I do the addition for this, 1 1 1 1 0 1 1 0, so the end carry out of this end carry you got as 0. So if I get a end carry as 0, the interpretation is x is less than y, okay, this is the interpretation. So this result which we are going to use in the algorithms. So what is the conclusion here? So what is the conclusion here? So the conclusion for this discussion is, right, okay, the conclusion for this discussion is, okay, so I want to compare two numbers in a digital system. I can use a digital comparator. So instead of using digital comparator, what I will do, right, I'll perform this, okay, x minus y. So this I will perform with instead of subtraction, I do the 2's complement of, so I will do this. Once I do this, what I get a end carry, right. If I get a end carry as 1, okay, the meaning is x is greater than or equal to y. If I get a end carry as 0, the meaning is x is less than y. So this is the result, okay. So this comparison, now what we are trying to do, the comparison, the comparator, instead of comparator using the digital comparator hardware, I can do this same, I can replace this digital comparator with the 2's complement subtraction, right. This is what I am telling, okay. This is one of the important results which you are going to use in the algorithms, right. So you should know this, you should understand this, try to understand this. So the next important result which you are going, you need to understand for before going to the algorithms is the, for example, in this generally what I told in the even in the fixed point format, you know that in the fixed point format or floating point format, for example, you take the fixed point format. So in the fixed point format, I want to represent a certain number, say. So if I want to represent certain number, I will represent the sign using 1 bit, the remaining bits I represent with the magnitude, okay. This is the sign magnitude form, right. This is the sign magnitude form. So where I represent the sign here, the remaining bits I use for magnitude, right. Similarly, I can represent using in the fixed point using 1's complement method. In 1's complement method, I will consider the entire magnitude, right, but this MSB represents the, what are the MSB bit, this represents the sign. Similarly, in the 2's complement method, you know how to represent the data. Similarly, here also the MSB bit represents the sign. So what is the meaning? In both the in all the three cases, if I represent sign as S, right, if also in the floating point, what is the floating point? Floating point representation. In the floating point, we use the, right, so we represent the sign, right, 1 bit. So these are the 1 bit, right, sign is always 1 bit. So here 1 bit, right, here also 1 bit, okay, here also 1 bit, and similarly sign here also 1 bit, right. Now here we have two things, one is the mantissa, okay, these few bits we represent the mantisas, right. Similarly exponent, so three things will be there in floating point, exponent. Now my in all this the common point is, if s equal to 0, this represents the positive number, okay. If s equal to 0, this represents the positive number. If s equal to 1, this represents the negative number. This represents the negative number. Okay, you know this, but my point is, my interest is, so if suppose two numbers are given, any of these two numbers are given, and I want to compare the signs. Okay, so for example, I have a two numbers are given, a and b. Two numbers are given, a and b. Suppose the sign of a is 0, sign of b is 0, right? Or if the sign of the a is 0, sign of a may be 1. Here the sign of a may be 1, sign of b may be 0, sign of both may be 1. Now what I need to do is, I need to compare the sign of these two numbers. I want to tell, right, whether the signs are equal. So in the first case, so for example, let me write this is the first case, second case, third case, fourth case. So in the first case, signs are equal. In the fourth case also, signs are equal. In the second case and third case, signs are not equal. But how to identify that in the hardware? How we do that? What I do is, we just connect the a sign of a. So this is, for example, the sign of a, let me call a as, sign of b, let me call for bs. So what I do, I connect this as sign, bs sign to an XOR gate. Okay, to an XOR gate. Okay, and perform the logic. So you know that, right? What is XOR gate? XOR gate is nothing but, if the signs are equal, okay, this will be 0. Signs are equal, this will be 0. The signs are not equal, this will be 1. This will be 1. So if the XOR gate output is 0, like if we perform AS XOR BS, if the XOR gate output is 0, we interpret that signs are equal. So similarly, if the XOR gate output is 1, we interpret that signs are not equal, right? Signs are not equal. So this way we can compare the signs of two numbers given, we are interested two numbers. So that two numbers sign can be compared with the help of an XOR gate. So in this video, what we have seen, we have seen the syllabus, what we need to cover in this unit. Also we have seen the definition, we have seen the syllabus. Okay, then we have seen what is the definition of an algorithm. Okay, how to represent an algorithm, like we use these rectangular boxes or this diamond shaped boxes. Similarly, we have seen how to perform comparison with 2's complement subtraction, right? With 2's complement subtraction, right? What is this thing, right? If carry equal to 1, okay, we interpret that suppose I want to compare two numbers, I perform this 2's complement subtraction, x minus y with x plus 2's complement of y. So if I do this, if I get a carry, the meaning is x is greater than or equal to y. If carry equal to 0, the meaning is x is less than y, right? That is the meaning, right? So finally I have seen how to compare the signs, of two numbers, right? How to compare the signs of two numbers and tell whether the signs are equal or signs are not equal. So this can be done with the help of an XOR gate. Okay, if the output equal to the XOR gate output equal to 0, means signs are equal, right? The XOR gate output is 1, signs are not equal. So this is the summary of this lecture. Okay, so hope we'll continue with this lecture series. Thank you. We'll meet in the next lecture.